Picture this. You're standing in a cave in southern Africa 35,000 years ago, and you're holding a baboon's leg bone. And some person whose name is gone forever, has carved 29 little notches into it. 29. Not random scratches, deliberate even, counted marks. And right there, in your hand, you're holding what might be the single oldest piece of mathematics on planet Earth. That's where this whole insane story begins. Okay, so here's the deal. The story of math is not boring. I know, you sat in a classroom and somebody made you memorize the quadratic formula while you slowly died inside. But that's not what this is. This is a human story. It's a story about obsession, about people keeping deadly secrets, about rivalries so vicious people literally got drowned, about a kid scribbling down the foundations of modern algebra the night before he died in a duel at 20 years old. If that sounds like your kind of thing, do yourself a favor and subscribe. We post these every single week. Hit the bell if you're feeling fancy. Cool. Now let me actually blow your mind. So back to the bone. It's called the Lubombo bone, named after the Lubombo Mountains between South Africa and Eswatini, where it was found in a place called Border Cave. And here's why it matters so much. 29 notches. You know what's roughly 29? The number of days in a lunar month. So a lot of people think this thing wasn't just somebody bored in a cave doodling. They think it might have been a tally, somebody tracking the moon, or tracking a menstrual cycle, or counting days until something. Which means 35,000 years ago, before writing, before cities, before agriculture, before basically everything you think of as civilization, a human being looked at the world and went, I need to keep track of this. I need numbers. And that's the thing about math, right? You and I tend to think of it as this abstract thing invented by old Greek guys in togas. But no, math is older than that, way older. Math is one of the first things humans ever did. Before we built a single building, we were counting. The Lubombo bone is the proof, sitting in your hand in that cave. Now, there's a cousin to the Lubombo bone, and it's even more famous. It's called the Ishango bone, found near the headwaters of the Nile in Central Africa, and it's around 20,000 years old. And this one is wild because the notches on it aren't just a simple tally, they're arranged in groups. And some people have looked at those groups and gone, hold on, are these prime numbers? Is this a doubling sequence? Is this an actual arithmetic table carved into bone? Now, to be fair, scholars argue about this a lot. Some say, yeah, it's clearly mathematical. Others say, slow down, it might just be a good grip for a tool. But here's the crazy part. Even the possibility that 20,000 years ago somebody was grouping numbers in patterns tells you that the mathematical instinct, the urge to find structure in numbers, is ancient. It's baked into us. And from there, things really start cooking. Let me explain. Fast forward to around 5,000 years ago, and we get to the place where math stops being scratches on bone and becomes a full-blown system. That place is Mesopotamia, the land between the rivers, modern-day Iraq. And the people we're talking about are the Sumerians, and later the Babylonians who came after them. Now here's the part that's going to mess with your head every single time you look at a clock for the rest of your life. The Sumerians counted in base 60. 60. You count in base 10, right? You've got 10 fingers, it makes sense. You count to 10 and start over. The Sumerians, base 60. And you might be sitting there going, why on earth would anybody pick 60? That's insane. And yeah, you'd call them crazy. You're not alone. But unfortunately, you're wrong, because base 60 is actually genius. Here's why. 60 divides really, really nicely. You can split 60 into halves, thirds, quarters, fifths, sixths, tenths, twelfths, 15ths, 20ths, 30ths, all whole numbers. Try doing that with 10. 10 only splits cleanly into halves and fifths, and that's about it. So for a civilization doing trade, dividing up land, splitting grain, tracking time, base 60 is a dream. It's a number that plays nice with division. And here's the wild part, you still use it. Right now, today. Why are there 60 seconds in a minute, 60 minutes in an hour? Why are there 360 degrees in a circle? Sumerians, Babylonians. A civilization that died out thousands of years ago is still controlling how you measure time and angles every single day of your life, and you never even noticed. Every time you check your watch, that's the ghost of ancient Mesopotamia tapping you on the shoulder. And that's why this stuff matters. Math doesn't die. It just gets passed down, hand to hand, century to century. Now, the Babylonians weren't just good at picking weird number bases. These people were serious mathematicians. And the single best piece of evidence for that is a clay tablet with a boring name and an absolutely insane backstory. It's called Plimpton 322. So here's the setup. Plimpton 322 is a Babylonian clay tablet, about 3,700 to 3,800 years old. It's named after a guy named George Plimpton, who bought it back in the 1920s. It's just a catalog number, 322, nothing fancy. It's a broken little slab of clay, covered in cuneiform, those wedge-shaped marks the Babylonians pressed into wet clay with a reed. And for a long time, people thought, it's a business record, some merchant's accounting, boring, except it's not. Let me explain. When mathematicians actually decoded the numbers on it, they realized this tablet is a list of Pythagorean triples. Now, you remember Pythagorean triples even if you don't think you do. A Pythagorean triple is a set of three whole numbers where the first two, squared and added together, equal the third one squared. The classic one is 3, 4, 5. 3 squared is 9, 4 squared is 16, 9 plus 16 is 25, and 5 squared is 25. Boom. It's the rule for a perfect right triangle. That's the Pythagorean theorem. A squared plus b squared equals c squared. You learned it. You probably hated it. And here's the crazy part. Here's the thing that should make you sit up. Plimpton 322 lists these triples, including big, complicated ones that you absolutely cannot just guess, about 1,000 years before Pythagoras was even born. 1,000 years. The guy the theorem is named after? The Babylonians were doing it a full millennium before he showed up. They knew the relationship. They had it written down on clay. They were generating these triples systematically, which means they understood the deep structure underneath, not just a lucky example or two. Which just goes to show the names we put on things in math are almost always wrong. We call it the Pythagorean theorem, but the Babylonians had it. We call it Arabic numerals, but they came from India. The history of math is one long story of credit going to the wrong person, and Pythagoras is Exhibit A. Which is hilarious, honestly, because the actual Pythagoras and his crew were about to give us one of the darkest, most dramatic moments in the entire history of mathematics. Speaking of which, let's talk about Pythagoras himself, because here's what they don't tell you in school. Pythagoras wasn't just a math guy. He ran a cult, a literal cult. Picture this. The year is around 500 BC, and you're in a town called Croton in southern Italy. And there's this charismatic, mysterious figure named Pythagoras, who's gathered a group of devoted followers around him, and they call themselves the Pythagoreans. And these people don't just do geometry, they have rules, bizarre rules. They believe in reincarnation, they have a whole philosophy, and famously, they're not allowed to eat beans. Beans. Don't ask, nobody fully knows, but the bean thing is real, and these people took it deadly seriously. But the core belief, the thing at the absolute center of the Pythagorean religion, was this. Everything is number. Everything. The whole universe, they believed, was built out of whole numbers and the nice, clean ratios between them. The harmony of music? Ratios. The movement of the planets? Numbers. Reality itself, at its deepest level, was rational. And by rational, I mean it literally. It could all be expressed as a ratio of whole numbers. One number over another number. That was the foundation of their entire worldview. That was their God. And that's where it all goes wrong. Because here's the thing about building your entire religion on an idea. What happens when the idea turns out to be false? What happens when one of your own people discovers a number that breaks the whole thing? Enter Hippasus. Now we get to the murder. Let me explain. Hippasus was a Pythagorean, one of their own. And according to the legend, and I want to be honest with you, this is legend, The details are murky, and historians argue about exactly what went down. Hippasus discovered something horrifying. He discovered irrational numbers, numbers that cannot be written as a ratio of two whole numbers, numbers that go on forever after the decimal point, with no pattern, never repeating, never resolving. And the way he probably found it is so simple it hurts. Take a square, just a basic square, with sides of length 1. Now draw a line from one corner to the opposite corner, the diagonal. How long is that diagonal? Well, by that very theorem we just talked about, 1 squared plus 1 squared is 2, so the diagonal is the square root of 2. And here's the gut punch. The square root of 2 cannot be written as a fraction. It is 1.4, 142, 135, and so on, forever, with no repeating pattern, no clean ratio, nothing. It is irrational. Now think about what that means for the Pythagoreans. Their entire religion said everything is whole numbers and ratios. And here's this number, the square root of 2, sitting right inside the simplest shape imaginable, a square, a thing they drew every single day, and it absolutely refuses to be a ratio. It's proof, undeniable proof, that their God was wrong, that the universe is not built purely out of nice, clean numbers, that there's something wild and infinite and messy hiding inside even the most basic geometry. And here's the part that's genuinely dark. The legend says the Pythagoreans could not handle this. This wasn't just an awkward math result. This was heresy. This threatened the very core of who they were. So what did they do? According to the story, they took Hippasus out onto a boat, out into the sea, and they threw him overboard. They drowned him. For telling the truth, for revealing that irrational numbers exist. Now, was Hippasus actually murdered? We genuinely don't know. Some versions of the story say he drowned at sea as divine punishment from the gods, not from his fellow cultists. Some say he was just exiled, kicked out, his existence erased. But the fact that this story survived at all, the fact that the ancient world passed down a tale of a mathematician being killed for a discovery, tells you something profound. It tells you that even back then, people understood that some truths are dangerous, that knowledge can shatter belief, that the square root of 2 was, to these people, a weapon aimed at the heart of everything they held sacred. And that's the thing that just goes to show how high the stakes felt. To you, irrational numbers are a Tuesday afternoon in algebra class. To the Pythagoreans, it was the kind of secret you'd kill a man to keep buried. Wild. Okay, let's catch our breath. Because so far we've gone from a bone in a cave, to clay tablets in Iraq, to a murder cult in Italy. And we're just getting warmed up. Because now we have to talk about the guy who basically built the rule book that math used for the next 2,000 years. And his name is Euclid. Now here's the year. It's around 300 BC. The place is Alexandria, in Egypt, which at this point is the intellectual capital of the entire world. There's this gigantic library there, the Library of Alexandria, the greatest collection of knowledge humanity had ever assembled. And Alexandria is buzzing with scholars from everywhere. And working in that city is a mathematician named Euclid. And Euclid does something that, honestly, changed how human beings think forever. He writes a book called The Elements. And The Elements is not just a math textbook, it's the math textbook. Let me put it this way. The Elements is one of the most printed, most studied, most influential books in the entire history of the human race, second only to the Bible by some counts. For over 2,000 years, if you learned geometry, you learned it from Euclid. Right up until the last century, kids were still being taught straight out of Euclid. 2,000 years of one book. Think about that. But here's what actually made it revolutionary. It wasn't that Euclid discovered a ton of new math, although he organized a mountain of it. The genius was the method. Euclid said, okay, let's start with a handful of things so obvious nobody could possibly disagree with them. He called these axioms and postulates. Stuff like, you can draw a straight line between any 2 points, or all right angles are equal to each other. Just basic, undeniable, obvious truths. A tiny handful of them. And then, and this is the magic, from those few obvious truths, using nothing but pure logic, step by step, he proved everything else. Every theorem, every result, built carefully on the ones before it, in an unbroken chain of reasoning back to those original obvious axioms. Nothing was just asserted. Nothing was, trust me, bro. Everything was proven. If you accepted the handful of obvious starting points, you were logically forced to accept all of it. This is the birth of the proof. This is the idea that you don't just believe something in math because it looks right, or because some smart guy said so. You believe it because it's been proven, chained by pure logic back to bedrock truths. And that idea, that one idea, is the foundation of all of math and a huge chunk of all of science. Euclid didn't just write a geometry book, he invented a way of thinking. And here's the crazy part. That way of thinking is going to come roaring back at the very end of the story when somebody proves that Euclid's beautiful dream has a limit. But we're getting ahead of ourselves. Hold that thought. Now, while the Greeks get all the glory in the Western telling of this story, I have to stop you right here because the rest of the world was absolutely killing it too, and a lot of times they were way ahead. Speaking of which, let's go to India. Because India gives us maybe the most important single idea in all of math, and you use it every second of every day without thinking about it. Zero, the number zero. Now you might be going, zero? What's the big deal about zero? It's nothing. That's the whole point. It's nothing. And that's exactly why it's so hard. Think about it. Other numbers count things. 1 sheep, 2 sheep, 5 rocks, 10 coins. But zero counts the absence of things. How do you write down a number for nothing? For a long time, civilizations just didn't. They had no zero. The Romans had no zero. Go look at Roman numerals. There's no symbol for nothing, which is part of why doing actual math with Roman numerals is a nightmare. And here's the deeper thing. Zero isn't just a placeholder, although that's huge too. Without zero as a placeholder, you can't tell the difference between, say, the number 25 and 205 and 2500. The zero is what holds the place and tells you the size. But Indian mathematicians went further. They treated zero as an actual number, a number you could add, subtract, multiply with, a number that lived on the number line in its own right. The big name here is a mathematician named Brahmagupta, working around 600 AD. And Brahmagupta laid down actual rules for how zero behaves. What happens when you add zero to a number? What happens when you subtract it? He even wrestled with the really nasty question, what happens when you divide by zero? Which, as anybody who's broken a calculator knows, is a genuinely deep and tricky problem that mathematicians are still careful about today. But the point is, Indian mathematicians took nothing and turned it into something. They gave the world a number for emptiness, and modern math literally cannot function without it. And those same Indian mathematicians, along with developing the number system we now use, the digits 0 through 9, the whole place value system, the thing you call Arabic numerals, which really should be called Indian numerals. They handed this gift westward, and the people who picked it up, refined it, and ran with it were the mathematicians of the Islamic world. And that's where we go next. The year is around 800 AD, and the place is Baghdad. And Baghdad at this time is the center of the world. There's an institution there, sometimes called the House of Wisdom, and it's pulling in texts and scholars from Greece, from India, from Persia, from everywhere, and translating and preserving and building on all of it. While a lot of Europe was going through a rough patch, the Islamic Golden Age was the beating heart of mathematics and science. And working in Baghdad is a man whose name you carry around in your pocket without even knowing it. His name is Al-Khwarizmi, Muhammad ibn Musa al-Khwarizmi. And I need you to really hear this name because it's going to sound familiar in a second. Al-Khwarizmi wrote a book around 820 AD, and the title of that book includes the Arabic word al-Jabr. Al-Jabr. It refers to the operation of moving terms around and balancing both sides of an equation, restoring and balancing. And al-Jabr, when it traveled into European languages, became one word you definitely know, algebra. That's where the word algebra comes from Al-Khwarizmi's book. But wait, it gets better. Remember I said his name should sound familiar? Al-Khwarizmi. When that name got translated and mangled through Latin over the centuries, it became another word you use constantly. Algorithm. Yeah, the word algorithm, the thing that runs your phone, your social media feed, your entire digital life, that word is literally a distorted version of one man's name, Al-Khwarizmi. So the next time some app shows you something and you mutter, "stupid algorithm," you're cursing a 9th century mathematician from Baghdad. He's everywhere. He's in your pocket right now. And what Al-Khwarizmi actually did was just as important as the words he gave us. He took math and made it systematic. Before him, solving an equation was often a one-off, a clever trick for one specific problem. Al-Khwarizmi laid out general methods, step-by-step procedures, for solving whole classes of equations. Do this, then this, then this, and you'll get the answer every time. Which, when you think about it, is exactly what an algorithm is, a recipe, a procedure that works every time. He turned math from a bag of tricks into a system of rules. And modern algebra, the stuff you sweated over in school with the X's and the Y's, grows directly out of his work. Now here's where the story starts to pick up speed and get really juicy, because we're heading into a period where math stops being a calm, scholarly pursuit and turns into a blood sport. People started keeping secrets. People started having public showdowns. People started straight up stealing each other's work. And the first great drama of this era happens in Renaissance Italy, and it's all about something deceptively simple, solving equations. Picture this. It's the early 1500s in Italy, and there is a specific math problem that has been beating the greatest minds for literally centuries. How to solve what's called the cubic equation. Now, you don't need to sweat the details, but here's the gist. You know how to solve simpler equations, the ones with an x squared in them. That's the quadratic formula, the thing they drill into you in school. But the cubic, the one with an x cubed in it, an x to the third power, that one had stumped everybody since the ancient world. People thought it might just be impossible. And then a mathematician named Scipione del Ferro cracks it. He figures out how to solve a certain type of cubic. Huge deal. Massive. And what does he do with this earth-shattering discovery? Does he publish it? Does he share it with the world? Nope. He keeps it secret. He tells almost nobody, just whispers it to a student on his deathbed. And why would he do that? Why hide one of the greatest math discoveries in centuries? Here's the thing, and this is so important for understanding this whole era. In Renaissance Italy, mathematicians made their reputations and kept their jobs through public math duels, literal contests. Two mathematicians would each give the other a list of problems to solve, and whoever solved more in public won. It was like a rap battle, but with equations, and your career and your honor were on the line. So if you had a secret method that nobody else knew, that was a weapon. That was your edge. You'd never give it away. You'd hoard it. So this secret method for the cubic gets passed around in the shadows, and eventually it lands with a guy named Niccolo Tartaglia. And Tartaglia is a fascinating, tragic figure. The nickname Tartaglia actually means the stammerer, because as a kid, during a massacre when French troops sacked his town, he got slashed across the face with a sword, and it left him with a speech impediment for the rest of his life. The man survived a sword to the face as a child, and he grew up to be a brilliant mathematician. Tartaglia independently figures out how to solve the cubic too, and now he's got the weapon, and he's winning his duels, and he's keeping the secret locked up tight. And that's where Cardano comes in, and this is where it gets dirty. Let me explain. Girolamo Cardano was another Italian mathematician, and honestly, what a character. This guy was a doctor, a gambler, an astrologer, and a mathematician, and he lived one of the most chaotic lives you can imagine. And Cardano desperately wanted that cubic solution. So he goes to Tartaglia and he begs, and eventually Tartaglia gives in and tells Cardano the secret. But, and this is crucial, he makes Cardano swear a solemn oath never to publish it. Swear it, a sacred promise. Tartaglia hands over his prized secret on the condition that Cardano keeps it locked away forever. So what does Cardano do? He publishes it. Yeah, he breaks the oath. In 1545, he puts out this massive, hugely important book on algebra called the Ars Magna, the Great Art. and the solution to the cubic is right there in it for the whole world to see. Now, in fairness to Cardano, and historians do go back and forth on this, there's some nuance. Cardano had found out that Del Ferro had actually solved it first, before Tartaglia, which Cardano felt let him off the hook for the oath. And he did credit both Del Ferro and Tartaglia in the book. But Tartaglia? Tartaglia was furious, absolutely livid. He felt betrayed, robbed, stabbed in the back, fittingly given his history. And the two of them got into a vicious public feud, slinging insults and challenges at each other for years. And here's the thing, that just goes to show what this era was really like. This wasn't gentle academics politely sharing knowledge for the good of mankind. This was cutthroat. This was oaths and betrayals and feuds and secret weapons. Math was personal. Math was war. And out of all that drama, that messy human drama of broken promises and wounded pride, came real, lasting progress. The general solution to the cubic, and then very quickly the quartic too, the equation with x to the fourth power, which one of Cardano's own students cracked. Centuries-old problems, finally falling in the middle of a soap opera. But here's a little seed I want to plant in your brain, because it's going to grow into something huge. When these Renaissance guys were solving cubics, they kept bumping into something that freaked them out. Sometimes, to get to a real, correct answer, the math forced them to take the square root of a negative number. And taking the square root of a negative number is supposed to be impossible. There's no normal number that, when you multiply it by itself, gives you a negative. So they'd hold their noses and use these impossible numbers in the middle of a calculation, and somehow the impossible numbers would cancel out and leave a perfectly good real answer at the end. They called them imaginary numbers, almost as an insult, like, these aren't real, this is nonsense. But it works, so whatever. Cardano poked at them and basically went, this is too weird, I'm not touching it. Remember that, imaginary numbers. They're going to become a very, very big deal. Now, moving on. Because we have arrived at the 17th century, and we've arrived at one of the most famous, most maddening, most beautiful stories in the entire history of mathematics. And it starts with a lawyer in France doodling in the margin of a book. His name is Pierre de Fermat. And here's the thing about Fermat, he wasn't even a professional mathematician. He was a lawyer, a magistrate, a government official. Math was his hobby, his side hustle. But he was so unbelievably good at it that he's considered one of the greatest mathematicians who ever lived, a founder of number theory, the deep study of whole numbers and their properties. And Fermat had this absolutely infuriating habit. He would come up with these incredible results, and then he'd tell people he'd proven them, but he wouldn't show the proof. He'd just claim it and move on, leaving everyone else to figure out how on earth he did it. And the most famous example of this, the single most famous margin note in human history, goes like this. Fermat was reading an ancient Greek math book, a copy of a work by Diophantus, and he was thinking about the Pythagorean theorem. Remember, a squared plus b squared equals c squared, and there are loads of whole number solutions, like our friend 3, 4, 5. Fermat asked himself a deceptively simple question. What if instead of squares you used cubes, or fourth powers, or any higher power? Could you find whole numbers where a cubed plus b cubed equals c cubed? Or a to the fourth plus b to the fourth equals c to the fourth? And Fermat claimed the answer was no, never. He claimed that for any power higher than 2, there are no whole number solutions at all. None. It just doesn't work. And then he wrote, in the margin of that book, in Latin, the most tantalizing sentence in the history of math. He wrote that he had discovered a truly marvelous proof of this, but, and here it is, the margin was too narrow to contain it. The margin was too small. That's it. That's all he gave us. He claimed to have a beautiful proof, said the margin was too small to write it down, and then he died without ever writing it anywhere else. And for the next 358 years, every great mathematician on Earth tried to prove what became known as Fermat's last theorem. And they failed. Over and over and over. The greatest minds in history, century after century, threw themselves at this problem. This simple-sounding claim a hobbyist lawyer scribbled in a margin, and it broke all of them. Now, here's the crazy part. The reason it's even called his last theorem is that it was the last one of his unproven claims still standing. All his other margin notes and challenges had eventually been proven or disproven over the years. This one, this stubborn one, just refused to fall. It became the great white whale of mathematics, the unsolvable problem, the thing that made and broke careers. And I'm going to leave you on the edge of your seat with that one for now, because the resolution of Fermat's last theorem is one of the great triumphs of the modern age, and it doesn't come until 1994, and it's a whole dramatic saga of its own. But just hold on to it. 358 years, a margin too small. We're coming back to it. Because now, while everyone's failing to prove Fermat, two of the biggest brains in human history are about to independently invent the single most powerful tool in all of mathematics, at almost exactly the same time, without talking to each other, and then spend the rest of their lives in a bitter, ugly war over who did it first. And what they invented is calculus. Now, calculus. Okay, so the word calculus makes people flinch, I get it. But here's what it actually is, in plain terms. Calculus is the mathematics of change, of motion, of things that are constantly shifting. Before calculus, math was pretty good at dealing with stuff that sits still, a fixed triangle, a static number, a shape that doesn't move. But the real world doesn't sit still. Planets move, cannonballs arc through the air, water flows, populations grow, everything is changing all the time, and the old math struggled to grab hold of that. Calculus cracked it wide open. It gave humanity a way to mathematically describe a world in motion. And I'm not exaggerating when I say that almost all of modern physics, engineering, and technology runs on calculus. Your car, your phone, the rocket that put people on the moon, calculus, all the way down. And the two men who invented it are titans. On one side, in England, you've got Isaac Newton. Yeah, that Newton. The apple, the gravity, the laws of motion. Newton developed his version of calculus in the 1660s, calling it his method of fluxions, because he was working on physics, on motion and gravity, and he needed a new kind of math to do it. But here's the thing about Newton. He was secretive and weirdly paranoid, and he didn't publish his calculus right away. He just sort of sat on it for years, using it privately. And on the other side, in Germany, you've got Gottfried Wilhelm Leibniz. And Leibniz was a genuine universal genius, a philosopher, a diplomat, a logician, all-around brilliant guy. And Leibniz developed his own version of calculus independently in the 1670s, a bit after Newton had privately worked his out, but Leibniz published first. And, this is important, Leibniz's version was better organized, with cleaner, smarter notation. In fact, a lot of the calculus symbols you'd see in a textbook today, that elegant, elongated S for an integral, the D's for derivatives, those are Leibniz's. His notation was so good we still use it. So you've got two giants, two countries, two versions of the same revolutionary idea, invented independently. And what should have been a beautiful story of human genius turned into an absolutely savage fight. Because the question became, who really invented calculus first? And it got nasty. Newton's supporters accused Leibniz of stealing the idea, of having seen Newton's unpublished work and copied it. Leibniz's side fired back. It became this huge international scandal, England versus the continent, a feud that consumed both men and their followers for years, and didn't even fully end when they died. And here's the kicker, the thing that just goes to show how petty even geniuses can be. Newton was the president of the Royal Society, the most powerful scientific body in England, and when a committee was formed to officially investigate who invented calculus first and settle the dispute, Newton, secretly, anonymously, wrote a big chunk of the committee's supposedly neutral report himself. He rigged the investigation in his own favor and then pretended it was an impartial verdict. That's how badly he wanted to win. The greatest scientist of his age, secretly ghostwriting his own court victory. And the historian's verdict today? They both did it, independently. Newton got there first in private. Leibniz published first and gave us the better notation. They each deserve credit. The whole war was, in a sense, pointless, a tragic waste of two brilliant lives spent feuding over something they could have shared. But it tells you something real about how discovery works. Calculus was, in a way, ready to be found. The ideas were in the air, the problems of physics were demanding it, and two minds independently reached out and grabbed it at almost the same moment. That happens in math more than you'd think. The same truth, found by different people in different places who never spoke. It's almost like these ideas are sitting out there waiting, and we just bump into them. Now, speaking of brilliant minds and tragic ends, I promised you a story at the very top about a kid who scribbled down the foundations of modern algebra the night before he died in a duel at 20 years old. And it's time, because we've reached the early 1800s in France, and we've reached one of the most heartbreaking, most romantic, most absolutely insane stories in the history of human thought. His name is Évariste Galois. Picture this. You're in Paris in the 1820s and 30s, and France is a powder keg, revolutions, political chaos, the monarchy and the republicans at each other's throats. And into this chaos is born a kid named Évariste Galois, who is, by any measure, a once-in-a-century mathematical genius. As a teenager, this boy is thinking thoughts that the leading mathematicians of Europe can't even follow. He's working on the deepest questions in algebra, questions about why some equations can be solved with a neat formula, and others, fundamentally, never can. But here's the tragedy of Galois, and it's almost unbearable. The world did not want to listen to him. He submitted his groundbreaking work to the French Academy of Sciences, the gatekeepers of mathematics, and it went wrong every single time. One famous story says the great mathematician Cauchy lost or misplaced his papers. Another time, he submitted a major work, and the mathematician reviewing it, Fourier, died before he could read it, and the manuscript was lost. When he finally got work in front of the judges, they found it too dense, too strange, too far ahead, and they rejected it. Imagine that. Imagine being a teenager holding ideas that will reshape mathematics forever, and nobody will even read your homework. And Galois did not handle this well, and honestly, who could? He got angry, he got political. He threw himself into the revolutionary movements of the time, got arrested, spent time in prison. He was a passionate, furious, brilliant, tormented young man who felt the whole establishment was against him, and frankly, it kind of was. And then we get to the duel, and nobody knows exactly what it was about. The most common story is that it was over a woman, some romantic entanglement, an affair of honor. Some people have wondered if it was political, if he was set up, but the result is the same. At the age of 20, Évariste Galois agreed to fight a duel with pistols, and the night before that duel, and this is the part that gives mathematicians chills to this day, Galois sat down, convinced he was going to die, and he wrote. He wrote all night, frantically. He poured out his mathematical ideas onto paper, scribbling in the margins, "I have no time, I have no time." He was trying to get it all down, everything in his head, every brilliant idea he'd never been able to get anyone to listen to, because he knew this might be his last chance to leave it to the world. He wrote letters to his friends, begging them to get his work to the great mathematicians of Europe, to make sure it wasn't lost. And the next morning, he fought the duel, and he was shot in the stomach. And he was left lying in the field, and he died the following day, at the age of 20. 20 years old. And here's the gut punch, the thing that makes this story echo through the centuries. Those papers he scribbled in a panic the night before he died, they contain the seeds of an entire branch of mathematics. We now call it group theory, and the broader framework is called Galois theory in his honor, and it is one of the absolute foundations of modern algebra. It's not some footnote. It underpins huge swaths of math and physics, and even the cryptography that protects your data online today. A panicked 20-year-old, scribbling against the dawn, convinced he was about to die, and he was right, left behind ideas so deep that mathematicians spent decades just unpacking them. And that just goes to show you something brutal and beautiful about this whole story. Genius doesn't always get recognized in time. The establishment rejected him, lost his papers, ignored him, and he died young and bitter and unread. And yet the truth he found was so powerful that it survived him anyway. It clawed its way out of those frantic midnight pages and into the heart of mathematics, where it lives to this day. Galois lost everything, his work, his recognition, his life, and still, in the end, he won. Because the math was real, and real math doesn't die. So let's take stock of where we are, because we've come a long, long way. We started with a baboon bone in a cave 35,000 years ago, with 29 notches counting the moon. We went to the Sumerians and their base 60 that still ticks inside every clock you own. We saw the Babylonians beat Pythagoras to his own theorem by 1,000 years on a clay tablet. We watched a man maybe get drowned for revealing that the square root of 2 refuses to be a fraction. We met Euclid, who taught humanity how to prove things, building a tower of truth from a handful of obvious bricks. We saw India conjure the number 0 out of nothing, and Baghdad give us the words algebra and algorithm from one man's name and one man's book. We watched Renaissance Italians swear sacred oaths and break them, feuding to the death over how to solve a cubic, and stumbling onto impossible imaginary numbers along the way. We met a lawyer who scribbled a margin note that tortured the greatest minds for 358 years. We watched Newton and Leibniz invent calculus on 2 different sides of Europe and then wage war over the credit. And we just stood at the edge of a field in France while a 20-year-old bled out, having left the foundations of modern algebra on a few sheets of paper written against the dawn. And here's the thing, every single one of these stories has the same heartbeat underneath it. Math isn't a cold, dead pile of formulas sitting in a textbook to torture you. Math is one of the most intensely human things we've ever done. It's people, real, flawed, obsessive, passionate people, reaching out into the dark and grabbing hold of truths that turn out to be bigger than they are. Truths that outlive the people who find them. Truths worth keeping secret, worth fighting over, worth breaking oaths for, worth, in the darkest moments of this story, maybe even worth killing for, or dying for. Hippasus and his square root of 2, Galois and his midnight pages, Fermat and his impossible margin, and the wildest part, we're not even close to done. Because everything we've talked about so far, all of it, was building toward a series of questions that would shake mathematics down to its very foundations. Questions like, can we prove absolutely everything that's true? Is there a limit to what math can know about itself? What actually happened with Fermat's 358-year-old margin note, and who finally cracked it in 1994? And who in the world is the mathematician who solved one of the hardest problems on Earth and then turned down $1 million and the highest honor in math and walked away from all of it? Those imaginary numbers Cardano was too scared to touch? They're about to become essential. That dream of Euclid's, that you can prove everything from a few solid axioms, somebody's about to prove that the dream is impossible, that in any system of math, there will always be true things that can never, ever be proven. And that one idea is one of the most mind-bending things any human being has ever discovered. But that, my friend, is exactly where we're heading next. Okay, so where we left off, I told you that somebody was about to take Euclid's beautiful 2,000-year-old dream, the dream that you can prove everything true from a handful of obvious axioms, and absolutely shatter it. But before we get there, we have to build the world that made that shattering possible, because the 1800s and the run-up to it are where math gets really, really weird, in the best way. This is where mathematicians stop just solving problems and start questioning the very ground they're standing on. So buckle up. Let's go back and rescue those imaginary numbers I told you to remember. You know, the ones Cardano poked at and went, nah, too weird, I'm out. The square roots of negative numbers that the Renaissance guys held their noses and used because they somehow worked. For a couple hundred years after Cardano, these things had a terrible reputation. The name itself, imaginary, was basically an insult. Even the great mathematicians treated them like a dirty trick, a calculation hack, something that wasn't really real, you just used it in the middle of a problem and hoped it went away. And then a few people came along and said, hold on, What if these numbers are real? Not real in the everyday sense, but real in the sense that they actually exist as legitimate mathematical objects, just as valid as any other number. And the man who really nailed this down, who gave imaginary numbers a home and made them respectable, was one of the absolute heavyweights of all time. His name is Carl Friedrich Gauss. Now I have to stop and tell you about Gauss, because this guy is, on a lot of people's lists, the greatest mathematician who ever lived. Full stop. They called him the Prince of Mathematicians. And the legend of Gauss starts when he was a little kid. The story goes that he was in a classroom, maybe 7 or 8 years old, and the teacher, wanting to keep the kids busy and quiet, told them to add up all the numbers from 1 to 100. 1 plus 2 plus 3, all the way up. Busy work, right? Should take a while. And little Gauss just sits there for a moment and then writes down a single number and says, "Done." The answer is 5050. And the teacher is stunned because the kid is right. And how did he do it in seconds? He saw the trick. He realized you could pair the numbers up. 1 and 100 make 101. 2 and 99 make 101. 3 and 98, 101. And there are 50 such pairs, each adding to 101. 50 times 101 is 5050. Boom. While everybody else was grinding away, adding one number at a time, this child saw the hidden structure underneath the whole thing. That's Gauss. That's the kind of mind we're talking about. He didn't compute harder, he saw deeper. And Gauss grew up to basically touch every corner of mathematics. He made monumental contributions to number theory, to geometry, to statistics, to astronomy, to physics. The bell curve, the normal distribution, the thing that describes everything from test scores to measurement errors, that's deeply tied to Gauss. And when it came to those embarrassing imaginary numbers, Gauss did something elegant. He said, "Let's stop thinking of numbers as living only on a single line. Let's give them a plane, a two-dimensional plane. Let me explain, because this is genuinely beautiful. You know the number line, right? It's just a straight line. Negative numbers to the left, positive to the right, 0 in the middle. Everything sits on that one line. Well, Gauss and a few others, like a surveyor named Wessel and an accountant named Argand who got there around the same time, independent discovery again, by the way, it never stops, they said, what if the real numbers run left and right, but the imaginary numbers run up and down, at a right angle? Now you've got a whole flat plane of numbers. Every point on that plane is a number, part real, part imaginary, what we call a complex number. And suddenly these imaginary numbers aren't some weird ghost you summon in the middle of a calculation. They're points on a map. They're as solid and visualizable as anything else. And here's the crazy part. Here's the payoff that makes this matter to you. These complex numbers, these supposedly fake, imaginary, who cares numbers, they turned out to be absolutely essential to describing reality. The deepest theory of physics ever devised, quantum mechanics, the thing that governs atoms and electrons and the entire microscopic world, literally cannot be written down without imaginary numbers. They're baked into the equations. Electrical engineering runs on them. Signal processing, the thing that lets your phone send and receive a clean call, runs on them. The numbers that mathematicians once sneered at as not real are now holding up the technological world you live in. Turns out the imaginary numbers were more real than anybody dared to believe. Which just goes to show you should never bet against a weird idea in math that refuses to go away. Now, while Gauss is busy being a god among mathematicians, something even more radical is brewing, and it strikes right at the heart of the most trusted, most rock-solid part of all mathematics, geometry. Euclid's geometry. Remember Euclid? The Elements? The guy whose handful of obvious axioms built all of geometry for 2,000 years? Well, it turns out one of Euclid's axioms wasn't quite as obvious as the others, and poking at it was about to blow the doors off reality itself. Here's the deal. Euclid had 5 postulates, his 5 starting assumptions. And the first 4 are dead simple, totally obvious, nobody ever blinked at them. You can draw a line between 2 points. You can extend a line. You can draw a circle. All right angles are equal. Easy. But the 5th one, the famous 5th postulate, was a clunky monster. It's usually stated in a way that boils down to this. Sheftam, if you've got a line and a point not on that line, there's exactly one line through that point that's parallel to the first one. Exactly one. Just one parallel line, no more, no less. Now, this fifth postulate always bugged mathematicians. It just felt wrong. It was too complicated, too wordy. It didn't have the clean obviousness of the other four. For 2,000 years, mathematicians were convinced this wasn't really a separate assumption at all. They were sure you could prove it from the other four, that it was a theorem in disguise. And generation after generation of brilliant people tried to prove the parallel postulate. And generation after generation, they failed. Every single one. And then, in the early 1800s, a few mathematicians independently, there it is again, had a genuinely revolutionary thought. They went, what if we can't prove it because it's not actually forced to be true? What if we just assume the opposite and see what happens? What if we build a geometry where there's more than one parallel line or no parallel lines at all? Surely that would lead to a contradiction, to total nonsense, and that would finally prove the postulate by showing the alternatives are impossible. Except that's not what happened. Let me explain, because this is one of the great plot twists in the history of human thought. The main heroes here are a Russian named Nikolai Lobachevsky and a Hungarian named János Bolyai, both working independently in the 1820s and 30s, and Gauss, it turned out, had quietly figured a lot of it out himself years earlier, but was too nervous to publish it because he knew how insane it would sound. These men assumed Euclid's fifth postulate was false. They built whole new geometries on that assumption, and those geometries did not collapse into nonsense. They were perfectly consistent, perfectly logical. They held together flawlessly. They were just different. This is the birth of non-Euclidean geometry, and it's hard to overstate how earth-shaking this was. For 2,000 years, everybody, including the greatest philosophers, believed that Euclid's geometry wasn't just a math system. It was the literal truth about physical space. It was how the universe actually was. It was as certain as anything could possibly be. And now these mathematicians had proven that you could have other geometries, equally valid, equally consistent, where parallel lines behave completely differently, where the angles of a triangle add up to more than 180 degrees or less, where space itself is curved. And here's the part that should make the hair on your neck stand up. This wasn't just abstract game playing, because decades later, when Albert Einstein came along and developed his theory of general relativity, his theory of gravity, he needed a mathematics that described curved space. Because that's what gravity actually is in Einstein's picture. It's the bending and curving of space and time itself. And the math was already sitting there, waiting for him. The non-Euclidean geometry that Lobachevsky and Bolyai and a later genius named Riemann had cooked up as a pure abstraction, as a what-if, turned out to be the exact language the real universe is written in. The geometry of reality is not the flat Euclidean geometry you learned in school. It's curved. Einstein proved it. And the math was ready 100 years early. Which, again, just goes to show this thing that keeps happening in our story. Mathematicians keep inventing stuff for no practical reason at all, purely because it's interesting, purely to follow the logic where it leads, and then decades or centuries later, reality turns around and goes, oh, actually, I needed that. The imaginary numbers became quantum mechanics. The curved geometries became gravity. It's almost spooky how often the pure, useless, abstract math turns out to be the secret blueprint of the cosmos. Now, all of this, the new numbers, the new geometries, was making mathematicians both excited and deeply, deeply nervous. And here's why. If your most trusted, most obvious assumptions, like Euclid's parallel postulate, could turn out to be optional, could be swapped out for the opposite and still work, then what was solid anymore? What could you actually trust? The ground was shifting under everyone's feet. And this anxiety drove math into one of its most ambitious and ultimately heartbreaking quests ever. The quest for absolute, total, unbreakable certainty. The quest to put all of mathematics on a foundation so perfect, so airtight, that nothing could ever go wrong again. And, spoiler, it does not end the way they hoped. But to understand the heartbreak, we need to meet the man who tried to count infinity. His name is Georg Cantor. And Cantor did something that, when he first did it, got him attacked, ridiculed, and called a corrupter of youth and a charlatan by some of the most powerful mathematicians of his day. What did he do? He took infinity, actual infinity, and he treated it like a thing you could measure. He asked a question that sounds almost childish, but turns out to be a bottomless pit. The question is, are all infinities the same size? And you're probably thinking, what? Infinity is infinity. It's just endless. How can one endless thing be bigger than another endless thing? That's the whole point of infinity. It doesn't end. And yeah, you'd call Cantor crazy for even asking. You're not alone. The mathematicians of his time called him crazy too. But unfortunately for your intuition, you're about to be proven wrong, and the way it happens is gorgeous. Let me explain. Cantor said, okay, how do we even compare sizes of infinite collections when we can't count them one by one because they never end? And he had a brilliant idea. He said, let's use matching, pairing up. Think about it like this. Suppose you walk into a huge theater and you don't want to count all the seats and count all the people. Instead, you just look around. If every person is sitting in exactly one seat, and every seat has exactly one person, and there's nobody standing and no empty seats, then you instantly know, without counting, that there are exactly as many people as seats. They match up 1 to 1. That's the trick. That's how you compare sizes without counting. So Cantor applied this to infinite sets. He looked at the counting numbers, 1, 2, 3, 4, and so on forever. That's an infinite set. Then he looked at other infinite sets and asked, can I match them up 1 to 1 with the counting numbers? And here's where it gets wild. He showed that a bunch of infinities you'd think are way bigger are actually the exact same size as the counting numbers. The even numbers? Same size as all the counting numbers, even though it feels like there should be half as many. The fractions, all of them, every possible fraction, also the same size as the counting numbers. He found a clever way to line them all up and match them 1 to 1. These he called countable infinities. But then Cantor looked at the real numbers, all the numbers on the continuous number line, including all the irrationals, all those endless, non-repeating decimals like the square root of 2 and pi. And he asked, can I match these up 1 to 1 with the counting numbers too? And he proved, with one of the most elegant arguments in all of mathematics, called the diagonal argument, that you cannot. It's impossible. No matter how you try to list the real numbers and match them to 1, 2, 3, 4, you can always construct a new real number that isn't on your list. Always. There are simply too many of them, which means, and here's the bombshell, the infinity of the real numbers is bigger than the infinity of the counting numbers. There are different sizes of infinity. Some infinities are genuinely, provably, larger than others. Infinity is not one thing. It's a whole tower of bigger and bigger infinities, climbing up forever. And here's the truly dizzying part. Cantor showed you can keep going, that there are infinitely many sizes of infinity, each one bigger than the last, an infinite staircase of infinities. That is one of the most mind-bending things a human being has ever discovered, and it came out of one man playing very, very carefully with the simple idea of matching things up. And the reward Cantor got for this masterpiece? He got savaged. A hugely influential mathematician named Leopold Kronecker, who happened to be one of Cantor's old teachers, hated this work with a passion. Kronecker thought infinity should never be treated as a finished, completed thing you could measure, and he blocked Cantor's career, attacked his ideas, called them dangerous nonsense. And Cantor, who was a sensitive man to begin with, suffered terribly. He fell into deep depression. He spent time in and out of psychiatric institutions for the rest of his life, and he died in poverty in an institution during the chaos of the First World War, his greatest work still controversial. But here's the thing that just goes to show how truth wins in the end. Today, Cantor's theory of infinite sets, called set theory, is considered one of the absolute foundations of all of modern mathematics. The thing he was ridiculed and broken for is now in the bedrock. One of the greatest mathematicians of the next generation, David Hilbert, famously said that no one would ever drive mathematicians out of the paradise that Cantor had created for them. Paradise. The work that destroyed Cantor's life became paradise for everyone who came after. That's the cruel, beautiful pattern of this whole story. And that name, David Hilbert, brings us right to the doorstep of the great crisis. Because Hilbert was the one who tried to save mathematics. Hilbert was, around the turn of the 20th century, the most respected mathematician in the world, the undisputed leader. And Hilbert had a dream, a grand, beautiful, ambitious dream. And it was basically the ultimate version of Euclid's old dream, supercharged for the modern age. Hilbert wanted to put all of mathematics, every single branch of it, on a foundation that was provably, perfectly secure. Here's what he wanted, and it's worth understanding because it's so reasonable, so noble, and so doomed. Hilbert said, let's take all of math and build it up rigorously from a clear set of axioms, basic rules, using strict logic. And then let's prove three things about this system. First, that it's consistent, meaning it never contradicts itself. You can never prove something is both true and false. That would be a disaster, because in math, one contradiction breaks everything. Second, that it's complete, meaning every true statement in mathematics can, in principle, be proven within the system. Every truth is reachable. Nothing true is left dangling, unprovable. And third, that it's decidable, meaning there's a clear mechanical procedure, an algorithm, that can tell you whether any given statement is provable or not. Think about how gorgeous that dream is. A mathematics with no holes, no contradictions, no unanswerable questions. A perfect, complete, self-contained machine of truth, where everything that's true can be proven and everything is decidable. Hilbert laid this out as the great program for mathematics in the 20th century. He rallied the troops. He famously declared, "In mathematics there is no ignorabimus. There is nothing we cannot know. We will know. We must know." That was the rallying cry. Math would become the one perfect, complete system of knowledge, the one place where certainty was total and absolute, and it was a great dream. And it lasted about 30 years. Because in 1931, a quiet, intense, 25-year-old logician from Austria stood up and with a single piece of reasoning brought the whole magnificent cathedral crashing down. His name was Kurt Gödel, and what he proved is, I think, one of the most profound and unsettling things any human being has ever discovered. So let me set the table carefully, because this is the climax we've been building toward since I first mentioned Euclid. Kurt Gödel was a strange and brilliant man. Soft-spoken, frail, deeply logical, and as he got older, increasingly paranoid in ways that would eventually become tragic. But we'll get there. In 1931, Gödel published a paper with one of those terrifying technical titles, but the ideas inside it are called Gödel's incompleteness theorems, and they took Hilbert's beautiful dream and proved that it was impossible. Not just unachieved, impossible, forever, for anyone. Here's the heart of what he proved, in plain language. Gödel showed that in any mathematical system that's powerful enough to do basic arithmetic, just regular counting, adding, multiplying, the stuff a child does, there will always be statements that are true, but that cannot be proven within that system. True, but unprovable. There will always be truths that the system can see are out there, but can never reach. Always. No matter how you build your system, no matter how many axioms you add, there will be true statements that slip through the cracks, that can never be proven from inside. Let that sink in, because it's the exact opposite of everything Hilbert wanted. Hilbert wanted completeness, every truth provable. Gödel proved that completeness is impossible. Math, any math rich enough to count, will always be incomplete. There will always be true things you cannot prove. And then he twisted the knife with the second theorem, which is somehow even more devastating. Gödel proved that such a system can never prove its own consistency. It can never prove, from the inside, that it doesn't contain a hidden contradiction. Think about what that means. Mathematics can never fully guarantee its own reliability. The system can't reach down and verify its own foundations. To prove a system is consistent, you'd have to step outside it into a bigger system, and then that bigger system can't prove its own consistency either, and on forever. There's no bottom. There's no final, self-certifying ground to stand on. Ever. Now, how on earth do you prove something like that? How do you prove that truth outruns proof? This is the genius part, the trick that makes mathematicians who understand it just sit back and stare at the wall for a while. Gödel found a way to make mathematics talk about itself. He invented a coding scheme, now called Gödel numbering, where every mathematical statement and every proof gets turned into a unique number. So a statement about numbers can secretly be a statement about other statements. Math could now refer to itself. And then, using this self-reference, Gödel essentially constructed a mathematical statement that says, in coded form, this statement cannot be proven. Read that again. He built a statement that asserts its own unprovability. And now you've got a beautiful trap. Because think it through. If that statement could be proven, then it would be false, since it says it can't be proven. And that means your system just proved something false, which means your whole system is broken and contradictory. But if your system is good and reliable, then the statement can't be proven, which means it's true. It's a true statement that cannot be proven. And there it is, the unprovable truth, sitting right inside arithmetic, impossible to remove. It's a cousin of those ancient self-referential paradoxes, like the liar's paradox. This sentence is a lie. If it's true, it's false. If it's false, it's true. But Gödel took that slippery wordplay and forged it into hard, rigorous, undeniable mathematics. He used self-reference not to make a cute puzzle, but to prove a permanent limit on what mathematics can ever do. And I want you to really feel the weight of this, because it's not just a technical result for specialists. This is one of the deepest discoveries about the nature of knowledge itself, full stop. For thousands of years, going all the way back to Euclid in that library in Alexandria, the dream was that with enough logic and enough rigor, we could in principle prove every true thing, that reason had no ceiling, that there was nothing we could not eventually know. Hilbert shouted it from the rooftops, "We must know, we will know." And Gödel, this quiet young man, proved that no, actually, there is a ceiling. There are true things, even about simple numbers, that can never be proven. Truth is bigger than proof. The universe of what's true will always be larger than the universe of what we can prove. There will always, always be more. And that just goes to show something almost humbling about the limits of the human mind, and of any mind. We built this perfect tool, logic, and we pointed it at itself and asked, "Can you do everything?" And the honest answer that came back, proven beyond any doubt, was no, I can't. There will always be more truth than I can capture. Hilbert's dream of a complete, self-certifying mathematics was dead. And weirdly, mathematicians didn't fall into despair over it. Most of them came to see it as one of the most beautiful and important results ever found. Because knowing the limits of your tools is itself a profound kind of knowledge. Gödel didn't break mathematics, he revealed its true nature. He showed us the edges of the map, and the edges turned out to be infinitely deep. Now, here's a heartbreaking footnote to Gödel, because the people in this story so rarely get happy endings. Kurt Gödel, the man who proved the limits of logic, ended his life in a deeply tragic way. He fled the chaos of Europe and ended up at the Institute for Advanced Study in Princeton, in America, where he became close friends with, of all people, Albert Einstein. The two of them used to walk home together, two of the greatest minds of the century, chatting about physics and philosophy and the nature of time. Einstein reportedly said that in his later years, he mostly went to the Institute just to have the privilege of walking home with Gödel. But Gödel's mind, so brilliant, was also fragile. He became consumed by paranoia, especially a terror of being poisoned. He would only eat food prepared by his wife. And late in his life, when his wife was hospitalized for an extended period and couldn't cook for him, Gödel, the supreme logician, the man who mapped the limits of reason, simply refused to eat. He starved himself out of fear, and he died. He weighed almost nothing at the end. The man who proved that no system can fully secure its own foundations was, in the end, undone by his own. It's one of the saddest stories in all of science, and it sits right next to one of the most magnificent ideas in all of science. And somehow, that feels exactly right for this whole twisted, beautiful saga. Now, that idea of self-reference and machines and procedures that Gödel was playing with, it didn't just blow up Hilbert's dream and then disappear. It planted a seed that, within just a few years, would grow into the single most world-changing invention in modern history. Because Hilbert had three parts to his dream, remember? Consistent, complete, and decidable. Gödel killed the first two, and the third one, decidable, the idea that there's a mechanical procedure to decide whether any statement is provable, was about to be killed by a young Englishman who, in the process of killing it, would invent the computer. Speaking of which, let me introduce you to one of the genuine heroes of the 20th century, in every sense of the word. His name is Alan Turing, and in the 1930s, Turing was a young, brilliant, slightly awkward mathematician at Cambridge, and he got obsessed with that third part of Hilbert's program, the decidability question, sometimes called by its German name the Entscheidungsproblem, the decision problem. The question was, is there some definite mechanical method, some step-by-step procedure, that could take any mathematical statement and crank out an answer for whether it's provable or not? A universal truth machine, basically. And to even attack this question, Turing had to do something incredible. He had to figure out what mechanical procedure even means in a precise mathematical way. What does it actually mean to follow a set of rules, step by step, mindlessly, like a machine? And so, to answer a question about the foundations of mathematics, Turing sat down and imagined a machine, a hypothetical, idealized machine. We now call it the Turing machine. Let me describe it because it's so simple, it's almost laughable, and yet it changed the entire world. Picture an infinitely long strip of tape divided into little squares, and on each square you can write a symbol or erase one, and there's a little head that can move along the tape, one square at a time, left or right, reading the symbol it's sitting on, maybe writing a new one, following a simple table of rules. That's it. A tape, a head, some symbols, a list of rules. That's the whole machine. And here's the staggering thing Turing proved. This absurdly simple imaginary device, this tape and head, can compute anything that can be computed at all. Anything. Any calculation, any procedure, any algorithm a human or any machine could ever in principle carry out, this little tape machine can do it, given enough time and tape. He'd captured the entire concept of computation in one dead simple model. And then he went further and imagined a universal Turing machine, one machine that could read a description of any other machine off its tape and then imitate it, become it, run any program at all. And if that sounds familiar, it should, because that is a computer. That is exactly, precisely, what your phone and your laptop and every computer on Earth fundamentally is. A universal machine that runs whatever program you feed it. Alan Turing, trying to answer an abstract question about the limits of mathematical proof, accidentally wrote down the blueprint for the digital age. Every single device you own, the entire internet, all of it, traces back to this young man imagining a strip of tape to settle a logic problem. The pure, useless, abstract math became the most practically important invention of the last century. There's that pattern again, and it never stops being astonishing. And what did Turing actually prove with his imaginary machine? He proved that Hilbert's decision problem has no solution. There is no universal procedure that can decide every mathematical question. He showed it through something called the halting problem. The question was simple. Can you write a program that looks at any other program and tells you whether that program will eventually stop running or whether it'll loop forever? And Turing proved, with beautiful logic, that no such program can possibly exist. It's impossible. There are questions about programs that no program can ever answer. Which means Hilbert's dream of decidability was dead too. All three pillars, consistency, completeness, decidability, knocked down by Gödel and Turing within a few short years. The great quest for a perfect, all-knowing mathematics was over, and out of its ashes rose the computer. And Turing's story, like so many in this saga, is both heroic and heartbreaking. When the Second World War came, Turing went to a secret facility in England called Bletchley Park, and he became one of the central figures in breaking the German military codes, most famously the Enigma machine, the device the Nazis used to encrypt their communications, which they believed was utterly unbreakable. Turing designed machines, building on his theoretical ideas, that could chew through the staggering number of possible code settings and crack the Enigma. Historians estimate that the code-breaking work at Bletchley Park shortened the war by years and saved countless lives, some say millions. This mathematician, with his abstract ideas about computation, may have done more to defeat the Nazis than entire armies. And how did his country repay him? After the war, Turing was prosecuted for being a gay man, which was a crime in Britain at the time. He was convicted, and to avoid prison, he was subjected to a brutal hormonal treatment, a chemical castration. This war hero, this founder of computer science, this man who helped save the free world, was humiliated and broken by the very country he'd saved. And in 1954, Alan Turing was found dead of cyanide poisoning at the age of 41. It was ruled a suicide. A half-eaten apple was found beside his bed. Decades later, the British government would finally issue a formal apology and a royal pardon, but of course it came far, far too late. The father of the computer, hounded to death by the world he helped build. So look at where this chunk has taken us. We took the imaginary numbers Cardano was afraid of and watched Gauss give them a whole plane to live on, and then watched them become the secret language of quantum physics. We watched Euclid's untouchable geometry crack open into strange, curved, non-Euclidean worlds that turned out to be exactly how gravity bends the real universe. We watched Cantor climb the infinite staircase of infinities and get destroyed for it, only to have his paradise become the foundation everyone now stands on. We watched Hilbert dream the most beautiful dream, a complete, consistent, decidable mathematics, a perfect machine of truth with nothing unknowable in it. And then we watched Gödel prove that truth will always outrun proof, that every system rich enough to count will always contain true things it can never prove, and can never even certify its own consistency. And we watched Turing, chasing the last piece of Hilbert's dream, invent the computer to kill it. And underneath all of it, the same heartbeat keeps pounding. These are people. Brilliant, obsessive, fragile, mistreated people, reaching into the dark and pulling out truths bigger than themselves, truths that cost them careers, sanity, and sometimes their lives. Cantor in the asylum, Gödel starving in fear, Turing dead beside a poisoned apple. And the truths they found outlived every bit of the cruelty, and they're holding up your entire world right now, this second, in the device you're watching this on. But here's what's wild. We still have unfinished business. Remember that lawyer, Fermat, and his maddening little margin note? The one that tortured the greatest minds for 358 years? We're finally going to find out who cracked it, and the story of how it got solved in 1994 is a thriller all on its own. A man working in total secret in his attic for 7 years, a triumph in front of the world, and then a horrifying discovery that the proof had a fatal hole in it. And after that, we're going to meet the strangest mathematician of the modern age, a Russian who solved one of the hardest problems on the entire planet, a problem worth $1 million prize, and then turned down the money, turned down the highest honor in all of mathematics, and walked away from the whole world into the woods. That's where we're going next. And trust me, it only gets better from here. Okay, so I've been dangling this in front of you for 2 whole chunks now, and it's finally time. Fermat's last theorem, the lawyer's margin note, the most maddening sentence in the history of mathematics. I have a truly marvelous proof of this, but the margin is too small to contain it. 358 years. Let me say that number again so it really lands. 358 years that humanity's sharpest minds spent throwing themselves at this one little claim and getting absolutely nowhere. And now I'm going to tell you how it finally fell. And I promise you, the real story is wilder than anything you'd make up. So let's recap the actual problem in case you need it. Fermat claimed that if you take the equation a to the power n plus b to the power n equals c to the power n, and you make n any whole number bigger than 2, then there are no whole number solutions. None. For squares n equals 2, you've got infinite solutions. All those Pythagorean triples like 3, 4, 5. But the second you go up to cubes or fourth powers or anything higher, nothing works. Ever. That's the claim. It looks so simple a clever teenager could understand the statement in 30 seconds. And yet proving it true for every single power, all the way up to infinity, broke everyone. And over those 3.5 centuries, the failures piled up, but they weren't worthless failures. Here's the thing about a problem this hard. Trying to solve it forced mathematicians to invent whole new branches of mathematics. Remember Euler, one of the most prolific mathematicians ever? He cracked the case for cubes, n equals 3. Other people knocked out specific other powers one at a time. A brilliant French mathematician named Sophie Germain, who, by the way, had to do her early work under a fake man's name because women weren't allowed into the mathematical world of her time, made huge strides and developed approaches that handled whole families of cases at once. But nobody could prove it for all powers at once. You can't check infinitely many cases one by one. You needed something deeper, something universal, and for 3.5 centuries that something just did not exist. And then we get to the hero of this story, and he is the most beautifully unlikely action hero you've ever heard of, because he's a shy, soft-spoken English mathematician named Andrew Wiles. And here's what you have to understand about Andrew Wiles. This problem found him when he was a 10-year-old kid. Picture this. You're 10 years old, you wander into your local library, and you pick up a book about math, and it tells you the story of this famous problem that a French lawyer scribbled in a margin 300 years ago. A problem so simple a child can understand it, but so hard that every genius in history has failed to solve it. And something inside you just goes, that one. That's mine. I'm going to be the one. And that's exactly what happened to Andrew Wiles. 10 years old, in a library in England, and he fell in love with Fermat's last theorem, and decided then and there that he would solve it someday. Now, most kids who say that grow up and forget about it. Wiles didn't. He became a professional mathematician, a serious one, at Princeton, but he kept that childhood dream tucked away, because honestly, working on Fermat directly was considered almost a joke. It was career suicide. It was the problem that ate people alive. Sensible mathematicians stayed away from it. So Wiles did respectable work on other things, and waited. And then, in the mid-1980s, something changed. Other mathematicians made a stunning connection. They showed that Fermat's last theorem was secretly linked to a completely different and very modern area of math, something involving objects called elliptic curves, and a deep, mysterious conjecture called the Taniyama-Shimura conjecture. And the connection was this. If you could prove this big modern conjecture about elliptic curves was true, then Fermat's last theorem would automatically fall out of it as a consequence. The ancient problem was secretly a corner of a vast modern theory. Solve the modern thing, and the 300-year-old ghost dies with it. And when Andrew Wiles heard about this connection, the childhood dream came roaring back to life. Because now there was a path. A real, legitimate, modern path to the summit. It was still an absolutely monstrous climb, proving the Taniyama-Shimura conjecture was itself considered maybe impossible, but it was a path. And here's where the story gets genuinely incredible, where it stops being a math story and becomes almost a thriller. Andrew Wiles decided to go after it, and he decided to do it in total, complete secrecy. Let me explain how unusual this is. Mathematics is normally a collaborative, social thing. You publish, you go to conferences, you share ideas, you bounce things off colleagues. Wiles did the opposite. He basically went dark. He told almost nobody what he was really working on. He retreated into the attic study of his house, and for 7 years, he worked on Fermat's last theorem in near total isolation. To avoid suspicion, he even cleverly released his backlog of older research in small pieces over the years, so it looked like he was still publishing normally, still a regular productive professor, while in secret, up in that attic, he was waging a private war against the most famous, unsolved problem in the world. 7 years of secret obsession. Think about the loneliness of that, the doubt. Nobody to tell when you hit a wall. Nobody to celebrate with when you have a breakthrough at 2 a.m. Just you and a problem that has crushed every person who ever came before you, and the constant nagging fear that maybe you're wasting your entire career. Maybe it can't be done. Maybe you're the latest fool to be eaten alive by Fermat. And he just kept going, building this enormous, intricate proof brick by brick in the dark. And then, in 1993, he was ready. He had it. Or he thought he had it. And the way he unveiled it is the stuff of legend. He went to a conference at Cambridge, back in England, and he scheduled a series of 3 lectures. And he didn't announce what they were about. He just started presenting, building, and words started to spread through the mathematical community that something was happening, that Wiles was up to something big. And in that final lecture, in front of a packed room, Andrew Wiles wrote the statement of Fermat's last theorem on the board, and he said, more or less, "I think I'll stop here." And the room erupted. People understood what they had just witnessed. After 358 years, the most famous problem in mathematics had, it seemed, finally been solved. It made the front page of newspapers around the world. A math proof on the front page. Andrew Wiles became, overnight, the most famous mathematician on the planet. The 10-year-old from the library had done it. Except, and here's the gut punch, the twist that makes this story truly great, he hadn't. Not quite. Let me explain. When you make a claim that enormous, the proof has to be checked, painstakingly, line by line, by other expert mathematicians, before it's officially accepted. It's called peer review, and for a proof this long and complicated, it ran to hundreds of pages of the most ferociously difficult mathematics imaginable. That checking process was intense, and as the experts pored over it, working through every step, one of the referees found something, a gap, a subtle, deep, serious error in one crucial part of the argument. The whole magnificent proof, the 7 years of secret work, the front page triumph, it hinged on a step that didn't actually hold up. Can you imagine? Can you imagine the horror? You've just stood in front of the world and announced you solved the most famous problem in human history. You're famous. You did it. The dream you've carried since you were 10 years old came true. And then, weeks later, a flaw turns up, and suddenly the whole thing is teetering, and the entire mathematical world is watching to see if the great Andrew Wiles actually did it, or just publicly humiliated himself. The pressure must have been beyond anything most of us could handle. And now the secret was out, the problem was famous again, and Wiles had to fix this flaw in public, under the gaze of the entire world, knowing that if he couldn't, his triumph would turn into the most spectacular failure in modern mathematics. So, Wiles went back to work. And this time, it was even more agonizing, because the easy elation was gone, replaced by gnawing fear that the gap might be unfixable, that the whole approach might be fatally broken. He brought in one former student, a mathematician named Richard Taylor, to help him, and the two of them attacked the error. For months, and nothing worked. Wiles later said it was the most intense period of his entire working life, and that he came right to the edge of giving up, convinced the gap couldn't be closed, that he had failed after all. And then, and this is the part that gives me chills, in September of 1994, after about a year of struggling with the broken proof, Andrew Wiles was sitting at his desk, about ready to admit defeat, taking one last look at why his original approach had failed. And in a flash, he saw it. He realized that the very reason his first method had failed actually contained the key to making a completely different, older method work, and the two approaches together, fused, plugged the gap perfectly. He described it as the most important moment of his working life, this sudden, incandescent revelation, so beautiful and so unexpected that he said he stared at it in disbelief for 20 minutes, and then walked around for hours, coming back to check it was still there, unable to believe it was real. The flaw was fixed. The proof was complete. Fermat's last theorem, after 358 years, was finally, truly proven. And that just goes to show something about the human spirit that I find genuinely moving. A childhood dream carried for 30 years, 7 years of lonely secret labor, a public triumph that turned into a public nightmare, a year of staring into the abyss of failure, and then, at the very last moment, salvation pulled out of the wreckage of the thing that had broken. Wiles got his proof. And here's a poignant little footnote. Fermat himself almost certainly did not have this proof. The mathematics Wiles used, elliptic curves and modular forms, didn't even exist in Fermat's time, not for centuries after. So what was that marvelous proof Fermat claimed he had in the margin? Almost certainly he was wrong. He probably had a flawed argument that he didn't notice was broken, the same kind of subtle trap that nearly got Wiles. The greatest problem in math history may have started with a brilliant man making an honest mistake and bragging about it in a margin. And that mistake launched 3.5 centuries of mathematics. Turns out, even being wrong can change the world. Now, while we're on the subject of legendary unsolved problems, I have to tell you about the moment, right at the turn of the millennium, when mathematics basically issued a bounty list. A list of the most important, most stubborn, unsolved problems in the entire field, with a literal cash reward attached to each one. Because this sets up the single strangest character in our whole story, a man who's about to make Andrew Wiles's secret attic look downright sociable. In the year 2000, a private institution called the Clay Mathematics Institute announced what they called the Millennium Prize Problems. 7 problems, 7 of the deepest, hardest, most consequential open questions in all of mathematics. And they put up a prize, $1 million for the solution to each one. $1 million per problem. These weren't random puzzles. These were the great white whales of modern math, problems that had resisted the best efforts of generations, problems whose solutions would reshape entire fields. Things with names like the Riemann hypothesis, which is about the deep, hidden pattern of the prime numbers, and is widely considered the most important unsolved problem in all of mathematics. Things like the P versus NP problem, which sits at the heart of computer science and asks, basically, whether every problem whose answer is easy to check is also easy to solve. To this day, 6 of those 7 problems remain unsolved. The Riemann hypothesis, P versus NP, still open, still waiting, the $1 million still sitting there unclaimed. But one of the 7 got solved, exactly one. And the story of who solved it and what he did afterward is one of the most astonishing and human stories in the entire history of mathematics. The problem was called the Poincare conjecture, and the man who solved it is named Grigori Perelman. Now, the Poincare conjecture, let me try to give you a feel for what it even is, because it sounds abstract, but the core idea is weirdly graspable. It comes from a field called topology, which is sometimes jokingly called rubber sheet geometry. In topology, you don't care about exact shapes or sizes or angles. You care about the deep, squishy properties of a shape that survive when you stretch and bend and deform it without tearing or gluing. So to a topologist, a coffee mug and a donut are literally the same shape, because you could mush one into the other, they both have exactly one hole. That's the kind of thinking we're talking about. Holes, connectedness, the fundamental nature of shape. Here's a way into the conjecture. Imagine you've got a sphere, the surface of a ball, and imagine you take a loop of string and lay it anywhere on that surface. You can always shrink that loop down to a single point while keeping it on the surface, sliding it around, tightening it, until it's just a dot. No matter where you put the loop, it shrinks to nothing. Now compare that to a donut. On a donut, if you loop your string around the hole or through the hole, you cannot shrink it to a point, it gets stuck on the hole. So the sphere has this special property. Every loop shrinks to a point that distinguishes it from shapes with holes. And it turns out, for ordinary two-dimensional surfaces like a ball's surface, this property of every loop shrinks basically tells you, yep, you're looking at a sphere. The Poincare conjecture asked whether this same beautiful idea holds true in 3 dimensions. Henri Poincare, a giant of French mathematics, posed it back in 1904. He essentially asked, in 3 dimensions, is every shape where every loop can shrink to a point fundamentally the same as a 3-dimensional sphere? It sounds simple. It is not. This question went unanswered for nearly 100 years. It became one of the most famous and important problems in all of mathematics, central to our entire understanding of shape and space, which is why it landed on that $1 million millennium list. Mathematicians had proven versions of it in higher dimensions. Bizarrely, the higher dimensional cases turned out to be easier, but the 3-dimensional case, the one closest to the space we actually live in, stubbornly refused to fall. And then, in 2002 and 2003, the math world got the shock of its life. A reclusive Russian mathematician, Grigori Perelman, who worked at the Steklov Institute in St. Petersburg, quietly posted a series of papers on the internet. Not in a fancy journal, not with a big announcement. He just uploaded them to a website where mathematicians share preprints, the way you might post something to a public folder online. And these papers, dense and brilliant and almost terse, claimed to prove not just the Poincare conjecture, but something even bigger that contained it, called the geometrization conjecture. Now, how Perelman did it is itself gorgeous, and it connects back to ideas we've already met. He used a tool called Ricci flow, building on the work of a mathematician named Richard Hamilton. And the idea of Ricci flow is almost poetic. You take your weird, lumpy, complicated three-dimensional shape and you let it flow. You let its geometry smooth itself out over time, kind of like how heat spreads through an object until the temperature evens out everywhere, or like how a wrinkled surface relaxes. The curvature flows and smooths and evens out, and as it does, the shape simplifies, revealing its true underlying nature. The big obstacle was that sometimes, during this flow, the shape would pinch and form nasty singularities, points where everything blows up and the math breaks down. Hamilton had gotten stuck on exactly these singularities, and Perelman's genius was that he figured out how to understand and control and surgically handle those singularities, how to cut them out and let the flow continue. He basically tamed the wild places where the equations exploded. It was a staggering technical achievement, drawing on geometry and analysis and physics-like intuition all at once. And here's where Grigori Perelman goes from being a brilliant mathematician to being one of the strangest and most fascinating human beings in this entire story. Because his proof was correct, teams of top mathematicians around the world spent years, literally years, carefully checking every step, filling in details, verifying the argument. And it held. Grigori Perelman had solved the Poincare conjecture, one of the 7 Millennium Prize problems, one of the most important problems in all of mathematics, a problem that had stood for nearly a century. He had done it. The $1 million was his. Worldwide fame was his. Every honor mathematics could offer was his for the taking. And he turned it all down. All of it. Every single bit. Let me explain, because this is almost hard to believe. In 2006, Grigori Perelman was awarded the Fields Medal. Now, the Fields Medal is the highest honor in all of mathematics. There's no Nobel Prize for math, so the Fields Medal is it. It's the ultimate recognition, given only to a tiny handful of mathematicians, and only to those under the age of 40. It's the dream of basically every mathematician alive. And Grigori Perelman became the first person in history to refuse it. He declined the Fields Medal. He didn't show up to the ceremony. He just said, in effect, "No thank you, I don't want it." And then, a few years later, in 2010, the Clay Mathematics Institute officially awarded him the Millennium Prize for solving the Poincare conjecture. $1 million, cash. His, free and clear, for a piece of work he had genuinely done. And he turned that down too. He refused the $1 million. He walked away from it. Now why? Why would a man who, by accounts, lived modestly, even in near poverty, in a small apartment with his mother in St. Petersburg, turn down $1 million and the highest honor in his field? And this is where Perelman becomes genuinely profound, even if you find him baffling. He gave a few reasons over the years, in his rare comments to journalists, because he mostly refused to talk to the press at all and basically vanished from public life. But the gist of it was this. He felt the mathematical community was, in his view, unethical and unjust. He was disgusted by what he saw as the politics, the credit grabbing, the way some people scrambled for recognition and prizes while doing less of the real work. He felt that others, particularly Richard Hamilton, whose Ricci flow he had built upon, deserved as much credit as he did, and that singling him out for the prize was unfair. He reportedly said that he wasn't interested in money or fame, that he didn't want to be on display like an animal in a zoo. And famously, he said something like, "If the proof is correct, then no other recognition is needed." Let that sit with you for a second. If the proof is correct, then no other recognition is needed. Think about everyone we've met in this entire story. Think about Newton secretly rigging a committee to win credit for calculus. Think about Cardano breaking a sacred oath to publish first. Think about the Renaissance mathematicians duct taping their secret methods to win public duels for fame and money. Think about how much of this whole saga has been driven by ego, by the hunger for recognition, by the desperate human need to be the one who gets remembered. And here comes Grigory Perelman, who solves one of the hardest problems on earth and looks at the $1 million and the highest medal in his field and says, no, the truth is its own reward. I did the math is correct, that's everything. The rest is noise. Whether you think he's a saint or a hermit or just a deeply unusual man, you have to admit there's something almost impossibly pure about it. In a story absolutely soaked in rivalry and ego and credit stealing and oaths broken for glory, the final great problem solver of the modern age turned out to be a man who wanted none of it. He solved the problem, and then he quietly withdrew from mathematics and from public life almost entirely, living simply, declining interviews, declining honors, declining money. He proved the thing, and then he let it go. And that just goes to show that this story, which started 35,000 years ago with a nameless person carving notches into a baboon bone in a cave, kind of comes full circle. Because that first mathematician didn't do it for $1 million or a Fields Medal either. They did it because there was something true and real and worth knowing in those marks, in tracking the moon, in counting the days. And here, at the cutting edge of the 21st century, the man who solved the Poincaré conjecture comes back to something like that same purity, the truth found for its own sake, the math correct and needing nothing else. Now, I don't want to leave you thinking modern math is all lone geniuses and addicts and hermits refusing prizes, because actually, the way math gets done today is changing in ways that would have blown the minds of everybody we've talked about. Remember Alan Turing and his imaginary tape machine? Remember how that abstract idea became the computer? Well, those computers have come roaring back into mathematics itself, and they're starting to do something that touches on one of the deepest questions in this whole saga. What does it even mean to prove something? Think back to the four-color theorem, which is a perfect example of this. Here's the problem. Imagine any map, countries, states, regions, whatever, and you want to color it so that no two regions that share a border have the same color. How many colors do you need, at minimum, to be able to color absolutely any map you could ever draw? And the answer, it turns out, is 4. 4 colors are always enough. This was conjectured way back in the 1800s, and like Fermat's note, it was one of those things that sounds simple and turns out to be brutally hard. It resisted proof for over a century. And then, in 1976, 2 mathematicians named Kenneth Appel and Wolfgang Haken finally proved it. But here's the controversial, mind-bending part. They proved it with the help of a computer. The proof involved breaking the problem down into a huge number of specific cases, nearly 2,000 of them, and then having a computer grind through and check every single one, far more than any human could ever verify by hand in a lifetime. And this caused an uproar, because for the first time, you had a mathematical theorem whose proof no single human being could fully check, top to bottom, with their own mind. You had to trust the computer. And that struck right at the soul of what mathematics had always been, going all the way back to Euclid in that library. The idea that a proof is a chain of reasoning a human mind can follow and verify and understand completely. Suddenly, there was a proof that was correct, that everyone eventually accepted, but that was, in a sense, beyond direct human comprehension. Was that even a real proof? Mathematicians argued about it fiercely, and in some ways, they're still arguing about it today. It opened a door that can never be closed, the door to a mathematics where machines are partners in discovery, where some truths are verified by silicon rather than understood by a single human soul. And that question echoes everything we've been talking about. Gödel showed there are truths we can never prove. Turing built the machine that became the computer, and now that computer is back, helping us prove things, but also forcing us to ask, all over again, what proof and truth and understanding really mean. The same questions, the same deep mysteries that drove Euclid and Hilbert and Gödel, just wearing new clothes. So look at the road we've traveled in this chunk alone. We watched Andrew Wiles carry a childhood dream for 30 years, vanish into an attic for 7, conquer a 358-year-old problem, watch it crumble in public, stare into total failure, and then pull triumph out of the wreckage at the last possible second. We saw mathematics put $1 million bounty on its 7 greatest unsolved mysteries, 6 of which still stand, waiting, including the legendary Riemann hypothesis. We met Grigory Perelman, who solved one of those 7 and then walked away from the money, the medal, the fame, and the entire mathematical world, because to him, the truth was enough. And we watched computers themselves enter the story, forcing us to rethink the very nature of proof. And through every single bit of it, the same heartbeat keeps pounding, the one that's been there since the very first notch on the very first bone. Human beings, reaching into the dark, pulling out truths that are bigger than they are, and being changed by them. Sometimes they grab fame, sometimes they refuse it. Sometimes the truth costs them everything, and sometimes it sets them free. But always, always, they reach. And we're almost at the end now, but not quite, because there are still some threads to tie together, some final mind-bending ideas about where all of this is heading, and one last look at the deepest question of all, the one that's been lurking underneath this entire story from the very beginning. Is math something we invented? Or is it something we discovered, something that was out there waiting, written into the fabric of the universe itself, long before the first human ever carved the first notch? That's where we're going to finish, and trust me, it's the best part. Okay, so I left you on the biggest question of all, the one that's been quietly haunting this entire story from the very first notch on that baboon bone in a cave. And here it is, straight up. Is math something we invented, or is it something we discovered? Did human beings make up mathematics, like we made up chess or the rules of a game? Or is math out there, real, eternal, true, whether or not anybody ever exists to think it, waiting in the dark for us to stumble onto it? Stick with me, because this question is way deeper than it sounds, and the answer, or the lack of one, is kind of the whole point of everything we've been talking about. Let me set up both sides, because honestly, you can feel the pull of each one. On the one hand, you've got the idea that math is discovered. The people who believe this are sometimes called Platonists, named after the ancient Greek philosopher Plato, who believed there was a perfect, eternal realm of ideal forms existing beyond the physical world. And the Platonist about math says, look, the number 7 was prime before there were any humans. 2 plus 2 equaled 4 before the first life crawled out of the ocean, and it'll equal 4 long after the last star burns out. These truths don't depend on us. We didn't vote on them. We can't change them. We just discover them, the way an explorer discovers a mountain that was always there. Mathematicians, in this view, aren't inventors. They're explorers, mapping a landscape that exists completely independently of the human mind. And here's the thing that makes this view so seductive, and it's something we've watched happen over and over in this whole story. Remember how many times the pure, useless, abstract math turned out to be the secret blueprint of reality? The imaginary numbers that Cardano was scared to touch became the language of quantum mechanics. The weird, curved, non-Euclidean geometries that Lobachevsky and Bolyai dreamed up as a pure what-if became the exact mathematics Einstein needed to describe gravity bending space and time. The Platonist looks at that and goes, see? How could we possibly have invented numbers that we didn't even understand, numbers we literally called imaginary as an insult, and then have the universe turn around and use them in its deepest laws? That's not invention, that's discovery. We keep finding that reality was built with the same math we thought we were just making up in our heads. The physicist Eugene Wigner famously called this the unreasonable effectiveness of mathematics, the spooky, almost miraculous way that abstract math, cooked up for no practical reason, keeps turning out to describe the physical world with perfect precision. Why should the universe care about our equations, unless, maybe, the equations were there first? But hold on, because the other side has a serious case too. The other view says math is invented. It's a human creation, a language, a tool we built. And the people on this side point out, look, math is full of human choices. We chose base 10 because we have 10 fingers. The Sumerians chose base 60. We invented the symbols, the notation, the definitions. We decided what counts as a proof. We even decided, way back with Euclid, what the rules of the game are. Pick some axioms, follow the logic. And here's their killer argument, and it ties right back to something we already talked about. Remember the parallel postulate, Euclid's fifth one? For 2,000 years, everyone thought it was forced, that it was the one true geometry of reality. And then mathematicians just changed it. They said, what if we assume the opposite? And they got a whole new, perfectly valid geometry. If math were this single, fixed, eternal truth, how could you just swap out an axiom and get a different but equally consistent math? Doesn't that prove we're choosing the rules? Doesn't that make it more like a game we invent than a landscape we discover? And then it gets even more interesting, because Gödel comes crashing back into this debate, the way he crashes into everything. Remember what Gödel proved? That in any system rich enough to do arithmetic, there are true statements that can never be proven within the system. Now think about what that does to this question. If math were purely something we invented, just a game with rules we made up, then how can there be true statements in it that we can't reach, that escape our own rules? It's almost like Gödel showed that math is bigger than any system we build to capture it, that the truth keeps spilling over the edges of our inventions. That sounds an awful lot like there's something out there, something real and infinite, that our human-made systems are only ever partially grabbing hold of. The Platonist loves Gödel for this. The truth is bigger than our proofs. The territory is bigger than any map we draw. And here's the honest answer to which side is right. Nobody knows. Genuinely. This is one of the great open questions in the philosophy of mathematics, and brilliant people line up on both sides, and the argument has been going for thousands of years and shows no sign of ending. And I actually think that's beautiful, because it means that the most basic question about the very thing we've been exploring this whole time, what even is math, is itself unsolved. We've used math to crack the secrets of the atom and the shape of space and the limits of logic, and we still can't fully agree on what it is or where it lives. There's something wonderfully humbling about that. Now, let me pull all of this together, because we have come such an unbelievably long way, you and I want you to feel the whole sweep of it in one go. So picture the entire journey. Picture standing at the very beginning, 35,000 years ago, in that cave in southern Africa, holding the Lubombo bone, 29 notches carved by a nameless human being tracking the moon. That's where math is born, not in a university, not in a temple, but in the hands of an ordinary person who looked at the world and needed to count it. And from that single bone, follow the thread forward. Watch it travel to Mesopotamia, to the Sumerians and Babylonians, who built base 60 and gave you the 60 seconds in your minute and the 360 degrees in your circle, ghosts of a dead civilization still ticking inside every clock you own. Watch them carve Pythagorean triples into clay on the Plimpton tablet, a full 1,000 years before Pythagoras was even born. Watch Pythagoras build a number-worshipping cult, and watch poor Hippasus maybe get thrown into the sea for revealing that the square root of 2 refuses to be a fraction. The first time in this story, but not the last, that a person paid a terrible price for a mathematical truth. Watch Euclid, in the great library of Alexandria, invent the idea of proof itself, the notion that you build truth up from a handful of obvious bricks, using nothing but pure logic, an idea so powerful it ran the world for 2,000 years, and still underpins how we think today. Watch India conjure the number 0 out of pure nothingness, giving math a way to write down emptiness itself. Watch Baghdad, in its golden age, give us the words algebra and algorithm, both born from one brilliant man, Al-Khwarizmi, whose mangled name is sitting in your pocket right now, running your phone. Watch the Renaissance erupt into mathematical blood sport, secret methods, public duels, sacred oaths sworn and broken, Del Ferro and Tartaglia and Cardano feuding over how to solve the cubic, and stumbling, almost by accident, onto those impossible imaginary numbers that nobody could yet understand. Watch Fermat, a lawyer doing math as a hobby, scribble the most maddening sentence in human history into a margin, and then die without explaining it, launching 358 years of obsession. Watch Newton and Leibniz independently invent calculus, the mathematics of change that runs all of modern physics and engineering, and then watch these two giants wage a bitter, petty war over who did it first, with Newton secretly rigging his own investigation. Watch Gauss, the prince of mathematicians, who saw the trick to summing 1 to 100 when he was a tiny child, give the imaginary numbers a home on a whole new plane, making them real and respectable, numbers that would one day become the language of quantum mechanics. Watch the impossible happen as Lobachevsky and Bolyai and Gauss and Riemann break Euclid's untouchable geometry wide open, building curved, non-Euclidean worlds that turned out to be the exact shape of the real universe, the math Einstein needed waiting for him a century early. Watch Galois, a furious, brilliant 20-year-old, rejected and ignored by the establishment, scribble the foundations of modern algebra through the night before a duel, writing, I have no time, in the margins, and then die in a field the next morning, his panicked midnight pages outliving him by centuries, alive in the cryptography that protects your data today. Watch Cantor climb the impossible staircase of infinities, proving that some infinities are bigger than others, and get destroyed by his peers for it, dying in an asylum while his ridiculed work quietly became the foundation of all modern mathematics, the paradise Hilbert refused to be driven out of. Watch Hilbert dream the greatest dream, a complete, consistent, perfect mathematics where every truth can be proven and nothing is unknowable, declaring we must know, we will know. And watch the quiet young Kurt Gödel walk in and prove, with breathtaking logic, that the dream is impossible forever, that truth will always, always outrun proof, that in any system rich enough to count there will be true things that can never be proven, and that math can never even certify its own consistency. Watch Gödel, who mapped the limits of reason, tragically starve himself to death in the grip of his own fear. Watch Alan Turing, chasing the last piece of Hilbert's broken dream, invent an imaginary tape machine to settle a logic problem, and in doing so, write the blueprint for every computer that has ever existed, then go on to crack the Nazi codes and help save the world, only to be hounded to death by the very country he saved, dead beside a poisoned apple at 41. Watch Andrew Wiles carry a 10-year-old's library dream for 30 years, vanish into an attic for 7, conquer Fermat's 358-year-old margin note, watch his triumph crumble in public when a fatal flaw appeared, stare straight into total failure for a year, and then pull salvation out of the wreckage in one incandescent flash. And finally, watch Grigori Perelman solve the Poincaré conjecture, one of the 7 great million-dollar problems of the new millennium, and then turn down the $1 million, turn down the Fields Medal, turn down the fame and the whole mathematical world, walking away into quiet because to him, if the proof is correct, no other recognition is needed. That's the story. 35,000 years, from a notch on a bone to a proof that some truths can never be proven. And here's what I want you to take away from all of it, the thing that's been pulsing underneath every single chapter. Math is not the cold, dead, lifeless pile of formulas they made you memorize in a classroom while you watched the clock. Math is one of the most intensely, achingly human things our species has ever done. It is people, flawed, obsessive, brilliant, jealous, generous, broken, magnificent people, reaching into the unknown and pulling out truths that are bigger and older and more permanent than they are. Truths worth keeping secret, worth fighting over, worth breaking oaths for, worth, in the darkest corners of this story, dying for and killing for. And truths that, in the end, always, always outlive the people who found them. Hippasus is gone, but the square root of 2 is still irrational. Galois bled out in a field at 20, but group theory is alive and protecting your secrets this very second. Cantor died alone and ridiculed, but his infinities are bedrock now. Turing was destroyed by cruelty, but you are watching this on a machine he dreamed into being. Every one of them reached into the dark, and every one of them grabbed something real, and every one of those somethings is still here, woven into the world you live in, into the clock on your wall, the phone in your hand, the GPS in your car, the very space and time you move through. You are, right now, completely surrounded by the discoveries of dead mathematicians, and most people walk through that invisible cathedral every single day and never even look up. But you did. You looked up. You followed this whole insane 35,000-year saga from a cave to the edge of the unprovable, and I genuinely hope you'll never look at a clock or a number or even the shape of space the same way again. Because the next time you check the time and see those 60 seconds, that's the Sumerians whispering to you across 5,000 years. The next time some app annoys you with its algorithm, that's Al-Khwarizmi reaching out from 9th century Baghdad. And the next time somebody tells you math is boring, you'll know the truth. That behind every dull little formula, there's a cave, a clay tablet, a murdered cult member, a duel at dawn, an attic, a hermit in the woods, and 35,000 years of human beings refusing to stop reaching into the dark. That's the entire history of math, not a textbook, a saga, the greatest, longest, strangest human story there is, written in numbers and still being written right now. Thanks for taking that whole journey with me. Now go look at a clock and feel that little shiver of recognition. I'll see you in the next one.